So our first topic is going to be heat expansion. So this is going to be when we apply heat to either a solid, a liquid, or a gas, its volume or length or area is going to expand. So in order to understand this, let's look at a solid first. So this is going to represent the atoms of the solid, which is going to be making up some kind of a lattice. And then each one of these atoms is going to have a positive nucleus, and then it's going to have a negative electrons that are in orbit around it. And so this one would have a positive nucleus, and then it's going to have negative electrons in orbit around it. So the forces that are holding this solid together are electrical forces. Opposites attract, and then like charges repel. So imagine this electron over here is going to see this positive nucleus and it's going to be attracted to it. And this electron over here is going to see this positive nucleus and is going to be attracted to it. And these two electrons are going to see each other and they're going to be repelled. So what's going to happen is that if you try to separate those two atoms, they're not going to like it because these electrons are attracted to these nucleuses. And so if you try to pull it apart, it's going to apply a force that's going to try to pull it back together again. If you try to push the two atoms together, it's not going to like it because then what's going to happen is that these two electrons are going to see each other and they don't like each other. So that's going to keep the two atoms from getting too close together. So if we push them together, they're going to want to push apart. If, on the other hand, we go in the opposite direction and we try to pull them apart, then it's going to try to pull it back together again. So we can visualize this as being springs. So you know that if you take a spring and you compress it, it pushes back apart. If you pull the spring apart, it pulls back together again. So we can imagine these electrical forces as being springs. So there would be a spring holding these two together, and there'd be a spring holding these two together, and there'd be a spring holding these two together. So imagine that there are springs that are holding this solid together. Okay, now we're going to put energy into those springs in the form of heat. So we're going to heat up the solid and we want to know what's going to happen. So imagine you got a slingshot, and if you have a slingshot and it takes a certain energy to pull it back this far. Well, what happens if you pull it back this far? It takes more energy. So as we add energy to this solid, what's going to happen is the atoms are going to be oscillating with a certain frequency. When we put in more energy, they're going to be oscillating even more. And so the solid here is going to expand. So that's what we mean by heat expansion. When we add energy to a substance, whether it's a solid, a liquid, or a gas, it's going to expand because it's got more energy. So how could we describe this mathematically? So we're going to say, imagine that you have a rod that is much longer than it is thicker. So the length of this rod is going to be L sub 0. And then we're going to apply heat to it, and we do that by changing the temperature. When we increase the temperature, we add more energy to the rod, and it's going to expand. So this rod is going to go over to here, and then the change in length is going to be delta L. So L sub 0 is the original length of the rod. Delta L is going to be how much does it change. Now it's also going to be expanding in this direction and in this direction, and it's also going to be expanding in this direction. But notice that this thickness here is much smaller than this one here, so we can basically ignore the expansion going this way and the expansion going this way and just concentrate on the length expansion over here. So our formula is going to be that the change in length of the rod is going to be dependent on what is the rod made of. So is the rod made of copper or iron? Is it, for that matter, is it made of rock, or is it a gas, or is it a liquid? So the substance is going to go into a constant here. So that constant is going to be given by the letter C, and then you notice I had to get kind of creative on my subscripts there. So I said L for length, expansion. So this is the expansion coefficient that goes in front of there. Then it's also going to depend on how long was the rod in the first place, and then it's also going to depend on how much do I change the temperature. So let's do a stupid example here. So what happens if I don't change the temperature? So you got this rod that's just sitting there, and I do not change its temperature, then what's the rod going to do? Well, 0 times anything is 0, so therefore the change in the length of the rod would be 0. I think you could have guessed that. But it's nice to know that the formula works as the change in temperature goes to 0. Now, we could also have a situation in which instead of having a rod, maybe you've got a cube. So something that is more three-dimensional like this. And so what's going to happen is as we change its temperature, not only is it going to be expanding this way and this way, but it's also going to expand this way, and then also in and out. So in this case, we're going to be talking about what is the change in volume of the object as we increase its temperature. Now this would have a different coefficient of linear expansion, or this time it's the coefficient of volume expansion, and it's going to be different than the coefficient of linear expansion. And notice that instead of this time it's going to be the change in volume is going to be equal to some constant, and then what was its original volume, and then how much did its temperature change. So it's a very similar looking formula. And then there's even a third version. So can you imagine what would be the third version of the formula, which is not used that often, but imagine that you've got a plate. So if you got a plate like that, it's not going to have much thickness to it, not much length, but it is going to have quite a bit of width and height. So the third version of the formula would be change in area would be equal to some constant, and then the original area, and then the change in temperature. But these are the two formulas that are going to be used most often. So here we have a table of different kinds of coefficients of expansion. So we got the coefficient of linear expansion, and then we've got the coefficient of volume expansions. And notice that the numbers are much, much bigger when you talk about gases. So when a gas, you heat up a gas, then that gas is really going to expand. And so you already know that because do you remember that equation of an ideal gas? Pressure times volume equals nKT. So if you increase the temperature, what happened to the volume? It increased. So that's a special example of this expansion type deal. So those are some different expansion coefficients. And so let's go ahead and do a word problem here. So imagine you got a steel bridge that is 200 meters long. So that's approximately 2 city blocks or 2 football fields long. And then the lowest and the highest temperatures it's going to be subjected to is going to be negative 40 degrees Celsius and 60 degrees Celsius. So how wide should the total length of all the expansion joints be? So you may not know what an expansion joint is, and so it's given in that picture there. So as you go across the bridge, you will notice that there are these plates that have like a jagged edge to them, and a lot of times that thing is covered over by a plate and then you drive across it. So what do you think is the purpose of these expansion joints? Well, if a bridge did not have expansion joints, then as it heated up, it would expand, and then the bridge might buckle. And then repeated heating and then cooling, heating and cooling would cause that bridge to bend, and then it could structurally weaken. So the idea of an expansion joint is to set some spaces in the bridge, so as the bridge heats up, the bridge can expand, and then those expansion joints are going to get closer together, and then that's going to help save the bridge. So we want to know, how big should we make these expansion joints for the bridge? So we're going to write down what you're given and what you're looking for. So the original length of the bridge is going to be 200 meters. And then let's assume that the change in temperature of the bridge is going to be when it's the maximum cold to when it's maximum hot. So we're going to take 60 minus negative 40. So remember to add those numbers together. 60 plus 40 is 100 degrees Celsius. And then it says that it's a steel bridge, so we can go back to that previous chart and find the coefficient of expansion for steel, and it turns out to be that number. Okay, then we're going to put it into this formula here and calculate the change in length of the steel, and you see it turns out to be about 2.24 meters, which is about this much. And so normally a bridge would have, let's say, 5 of those expansion joints. So that means that we would take that number, 0.24, and then divide it by 5, and then that would be how much each one of those expansion joints would have to be able to expand, which might be only about 5 centimeters, so about this much. So very important that bridges have this so that they don't buckle whenever you heat them up. Okay, let's take a break, and when we come back, we're going to talk about water and how it is the exception to the rule.